Okay. All right. Well, pausing. Yeah. So this is Coffee Compiler Club. I'm recording. You're all live. If you don't like it, bail out now. I have an open mic policy, but just ask you to keep your mic muted if you're not talking, just to avoid background noise. I'm suspecting there'll be fewer people this go around. Last go around was pretty busy. There were like 20, 25 people at the peak there. It was it was actually a pretty good one. I guess the Asian version wasn't as good, but the Friday morning round of discussions was a lot of fun. That was good. And I don't have any agenda, and there's nothing going on, so people have to make up their own grief. And so now whatever. Say it again, Cameron, on camera. Semantic versioning. What the hell?
Oh yeah. So I'm working with. We adopted semantic versioning a couple years ago as the basis for the language's versioning capabilities for module versioning and whatnot. And there's this question that comes up, which is, if I have two versions and I say I need version 2.5.1 and I have this other version, does it satisfy that version? And versions are not a totally ordered set. I don't know anything about math, so pretend I do when I use words like that. What's the relationship between, say, 2.5.1 and 2.6? And there's absolutely no relationship, right? You can't tell which one came before the other, which one came after the other. You can't tell.
They were ordered that way.
What's that?
It was in theory an order.
Well, think about it this way. I could have a 2.5, and then I could come out with a 2.6, and then someone could report a bug on 2.5, so I could release a 2.5.
There's no time order. There's semantic ordering, but no time order. Yes.
There's a loose ordering in that that 2.5.1 and 2.6 both came after 2.5.
Well, that's the time ordering piece. I still claim there's supposed to be a semantic ordering of some kind where 2.6 is like upwardly compatible, but not downwardly compatible with 2.5. And 2.5.2 is supposed to be downwardly compatible and upwardly with 2.5, but not with 2.6, something like that.
I hate semantic versioning. I think I tried to come up with versioning schemes that would be worse, and I could think of two. One of them is having all versions have the same name, so no versioning at all. That's worse than semantic versioning.
I've seen that, yeah.
And the other is random numbers that are not necessarily increasing.
So like get SHAs.
Yes, but that has, yeah, I guess, yes. So the problem with semantic versioning is that, which is worse, I think, than just incrementing the number, is that it tries to capture a semantic meaning that is impossible to do with just a short number. So let's say you're supposed to increment the major version when you make a breaking change. Mm-hmm. But how do you know the change is breaking?
Exactly.
And does it matter how many people you affect? Because
there's a difference there in that what you intend and what it claims the spec is very hard to validate that that's what you did. So you could claim that if you failed to break, that you had a bug in your implementation. You either should have not bumped the version or you should have made a change that was supposed to be breaking.
And also sometimes you say, so in most cases, what people do is say, okay, we increment when we make a breaking change to the public API. But that is something that you technically should never do. And when you do it in certain cases, so for example, in Java, we don't use semantic versioning, but so we increment the version every 6 months, but we say that then we're allowed to make changes to the specification. And people think that changes to the specifications have the potential, a greater potential for breaking stuff than just bug fixes. But in practice, that's just not true. What happened was in Java 11.2, sorry, there was a bug fix, a security fix even, I think, and it was also an 8U to 12 or something, that changed the way that class initializers are compiled. And it slowed them down potentially by a factor of 1 million, some of them.
Class initial, what?
Yes, I'll find the link.
Well, that's almost as slow as what we have now.
And that ended up breaking more code than any major, API change. So it's very hard to get it right. So I think it's better to just
anytime you slow something down by a factor of 1,000, shit breaks. That's a breaking change. Yeah.
Yeah, but it was a security fix. Nobody realized the importance. I'll try to find a link for that.
I remember the screaming that went around when string changed to substring to not the substring. I remember it now. We talked about it some while ago, and I was trying to replace it, but I remember hearing the screams of pain. There were folks who cared a lot one way or another, but it was effectively a breaking change because it was a resource consumption change.
Yep.
It was a major resource consumption change. Some things took a lot less memory, some things took a lot more, and if you took a lot more, you died. And that, there's your breaking change. Computation stack. So this is in the chat now. I have to go, do the thing. Oh my God. Oh, so long ago at Sun and JITting, and we were trying to do shit like, trying to do shit with when do you JIT code, and so the CL init could, while the class was not yet initialized, could make objects and call into code that would be very hot and want to get JITted. But the JIT didn't have a way at that time to distinguish that the class it was JITting on had not yet been completed, which meant that there were some other things that were not yet initialized, classes were not yet initialized, and I had to have you could call out, there was a thread hack that went in there that I ended up JITting in code that would detect that you were coming in from the CL init thread, and then you were allowed to use the JITted code. And if you were the wrong thread, that is to say, you got a hold of the published object while the class was not yet initialized, and you wanted to run the JITted code, you had to not until the first thread completed the JITting and the JITted code and completed the CL init. So the jitter had it was a secret backdoor to run JITted code from a remote thread before you finish the CL init, and that broke the spec. And it just went round and round and round and round. Why is this initializer slow? Sorry, I stopped to stare at it. Not inlineable. Yes, no shit. Everything's not inlineable in the CL init except by the thread running the CL init itself, because some other things don't get initialized in the proper order. I don't remember all the hell. Yeah, hotspot is not inline methods of initialization. That is not strictly true, or it wasn't true back in my day, but it started out being not true. And then it was true because CL inits were running. Doug Lee was running all kinds of shit in CL inits all the time. Big programs run their entire life inside the CL init. So we had to go JIT. Okay, so then that opened this back door where a non-CL init thread could get a hold of the JITted code, where if he's an interpreter, he took a lock and he just stalled. But the JIT didn't do it, so I had to have a thread-specific, class-specific lock taken, and other threads would stall. It was a giant pain in the butt. But you got to having JITted code only for the CL init thread and not for other threads with a
They didn't really design
lock.
class initialization until years after Java was released, and that was a fundamental mistake. It's always better to design before you build it than after.
Yeah, well, that's the history of all languages everywhere. It was a cool hack. I threw it. I used JavaScript. Right? I threw it out in 2 weeks. Oh, it's really cool. Oh gosh, it needs a few things. Let's add some more. Let's add some more. Let's add some more. Oh, pretty soon you got kitchen soup. Whatever. And wouldn't be better
I like that.
to start, but no one's going to design it from the start unless I know it was going to be the next big thing.
Anyway, so there was a bit of code here that took, I think, 540 milliseconds in Java 11 and 20 minutes in 11.1.
Right. I'm looking at why is it all bailing out to the interpreter? Yes, root method of the compile. Don't do heavy comps. Yeah, right. So this would be Doug Lee testing fork join by writing a CL init, did something quick, and then did all his calculations from inside the CL init. And that was the original original reason for what I just ranted on, you have to play stupid games to meet the spec. Yeah, because the spec's a mess there. One thread, the thread who starts the CLNet, he can block in a CLNet, and the block can be taken by another thread who runs other things, but no other thread is allowed to run the CLNet code except the thread that started the CLNet. And that can lead to deadlocks, and it can lead to, well, in my case, all kind of funny locks I had to force.
Right. Anyway, that was a sidetrack. I want to say it's very hard to, it's very hard to express. So what you want, if you wanted to express something semantic in a version, is what would be the probability that the average user would have to change their code in order to support the new version? And that is very hard to express with a short number, if at all possible. So that's
yeah,
why
I guess I wouldn't claim that you wanted to think about it that way, but maybe you do. Like, I don't want to go probabilities on my users, because that only makes sense if I have enough users to have probabilistic numbering. But also, that's not what people care about per se. They want to know, looking at it, whether or not it's going to mess with them or not.
Right.
Okay, Max, you don't have an email to Zoom mapping. Let me see if I can send me a private message on chat there, Max, with your email, so I can just map them, trying to figure out who shows up. And I don't know if Max can hear yet either, so let me go send hit chat. I can't do it. There it is.
So one of the reasons that versioning is so important for us is we actually, the binary, our IR is actually versioned. So when you pick up an IR file, it'll have every version that you currently support inside of it, including your test code, including debug support, whatever you want to include in there. You can obviously strip any of that out that you don't want in there, but the benefit of that is that you don't have to download 63 different files to test 63 different versions. You download one library, it has all those versions in it, and then your testing tools, for example, can automate whatever versions of that you want to support. You can automate the testing against all those versions, in parallel, live.
What language are you working on?
Ecstasy.
Is it done by some company?
Yeah, my company. So
you're looking at it right now. Oh, technology, gotcha. Sorry, that was maintenance.
So anyway, when you're putting together a type system, if you have a bunch of different libraries, they may have version dependencies across those libraries with each other. You may have version dependencies on some of those libraries, so it becomes it's actually a NP complete problem to try to figure out.
It's a hard open problem.
Yeah.
Yeah. Usually I do big projects. First thing is no external libraries, or I dribble them in very carefully and very independently.
No. But I'm talking about building a language that people will build libraries in.
No, I get it. No, right. So that all worked well. My theory of no external libraries, until I hit the land of JavaScript and doing mobile development in React Native and web development in React. And then you just had to pull in the freaking kitchen soup, and they all had weird dependencies. They all lied about their dependencies with each other, and they all tried to over dependency the next guy. Just a complete disaster.
I've actually solved quantum encryption.
Yes.
So the way you do it, if you want to defeat the quantum computers trying to decrypt your stuff, is you use NPM as your noise generator.
Holy shit.
In fact, you only have to pull one number. You just have to pull the current number of packages in NPM, and it changes so fast.
Yes.
Like, you never run out of random.
Yeah, yeah. I can't count the number of times I had to wipe my npm cache clear because it was corrupted and reload the whole damn ball of wax over and over and over again.
You know what it makes me think of every time I deal with JavaScript or NPM or anything like that? It's one of those experiments from like the 1970s, like what's the smallest instruction set you could make and still build everything out of it. And it's like, hey, look, I can do a Turing machine with 5 instructions. It's like, hey, great, here's 1,000,000 libraries built with 5 instructions. And it's almost like what it feels like. You know, everything is built from this tiny number of,
Well, then they just keep layering and layering them.
That's right.
And most of the layers seem to not add any useful feature. Somehow I needed this layer over that layer because I needed to compute my new semantic versioning number.
I'm fairly certain that if actual intelligence arises in a computer, it will be in JavaScript.
Well, that goes to the primordial soup argument of just a large enough.
Exactly, and it's organic. It is, in every horrible sense, organic.
Oh my God! All right. There were some fun things that came out of that JavaScript experience that I would take away and say that was cool if I could figure out how to make it behave. But there were a whole lot of like useless disasters where I just went round and round and round on the interwebs trying to sort out how many other people had this problem that no one ever heard of before and what the hell did they do about it. Never used Stack Overflow so much in my life. It's done now. Thank you very much.
Well, you had to use Stack Overflow because it was new for you.
No, I mean, Java was new. I never had to use Stack Overflow, but maybe that's not fair. And of course, it wasn't around when doing C and Fortran and a bunch of other things. And I poked at it occasionally throughout the years. And then JavaScript came, and it wasn't that it was new. It was that it wasn't JavaScript. It was the layer upon layer of languages to implement shit like React and React Native that were not just new, but like constantly changing. So this is just as Cameron was saying, they're constantly changing, constantly out of sequence with each other, constantly somehow broken. Everyone says, oh, this bug got fixed in that version, but you have to hook up this other thing, hook up with that thing, and with that thing, and then but my problem went away then, and maybe it'll go away for you too, right? That's how it always ended on Stack Overflow. Blah, 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 reload version, and my problem went away. No root cause, nothing, just like I scrambled the scramble soup enough, the bug went away, done. Don't touch, walk away.
I mean, isn't that kind of how machine learning works?
No, machine learning has some mathematics that drives you in a solution direction, where Stack Overflow can run you in circles endlessly.
Yeah, there's a gradient in machine learning.
There's a gradient. There's only grading in JavaScript. There's no gradient. This is the whole, make America great again. With
interestingly, for the first time in well over 10 years, I ran into a Java C bug this week. I think with JDK 11, I can't remember.
Java C bug, oh my God.
Yeah.
How do you even know that it's a bug?
Because if you expand the line into 2 lines, it works.
Oh, okay. Wait, 2? Really? Was this like the string thing or something? What the hell?
No. It was an array access off of a method result. And
really?
Yeah. So if you split it into 2 lines instead of 1 line, it worked.
It worked. The new line? What the hell?
And since I've written Java compilers and since I contributed to the JLS, I'm pretty sure I know.
Oh, really?
In this particular case, which was supposed to work. Yeah. What's that?
Did you report it?
No.
The reporting overhead's too high for a lot of these.
The reporting overhead is too high.
Yeah, if I had a clicky link in my Xterm window that would just report, I just click it, but nothing else. I'll do that. Otherwise, I'm like, fuck it. I'm fixing my bug and moving on.
Let me tell you, Chris. If you tweet it and we know you, we'll take care of it. We know you.
maybe that might be low enough. There is this thing.
I saved it, so I can tweet it.
Yes, yeah, you can do it. Yeah, totally.
So what we do is in Java, you can say if true, if false. So what we do is we take the code, because someone will come along and fix it later, which will break it. So we if false the code, and then else the workaround, so that a developer will come and look at it and say, what the hell? And it just gives them enough time to slow down and not accidentally fix it.
Yeah. Yeah, I've had a lot of code where I had it specifically a certain way, and a junior engineer came along and tried to embetter it. And I had to go unwind and then give them the hard lesson as to why the hell it is that way. And I never came up with a good answer. Like some places I can throw down an assert that says, you don't fucking need a null check here, although I can't express it in the language. Quit writing null checks in. And, because then the guy says, well, then it can throw a null pointer exception. So I wrote throws null pointer, and then I have to catch it. And then he tries to catch it someplace. He can't test it because it never throws. But if you were to run his catch code, it would just break another way. And it's like, stop. Back up. No. There's an invariant. Learn the invariant. What other random hacks? So here's another one. I had a guy, I had AST as abstract syntax tree for all you compiler nerds. Capital A, capital S, capital T. And some point I got the giant putback that said capital A, little st. And I said, why? What the hell? Bulk rename of this giant class and everything in it. And he was just like, oh, and he just didn't know. Same guy, super prolific, super misinformed, eager and not sure where to go here. I had all those ASTs had all these tree nodes for doing expressions in the primitives in the compiled language. So they're all boilerplate. So there's 20, 30 subclasses. They all have a pile of boilerplates. The name of the node, it's an add, it subtracts, it multiplies. It's bulk array for H2O. It's bulk array math for H2O. There are associativity rules, and there's 15 other little one-liner things on all these classes, plus something with semantic meaning that was interesting. And all the little one-liners I just threw out in one line, literally, say overload, int, priority, whatever thing, returns a 3 or God knows what, right? The name is this. And he came through and had to go break them all out so they all had proper spacing on the lines. So then the one-liner for an entire subclass describing a certain primitive was backed line by line by line by all the other identical primitives that changed very, very slightly. And you could see columnar wise, they were all identical, except they had the change in the string name and which implementing function or whatever random thing. And then he broke them all out. So they all stretched vertically on and on and on, but you lost the 2D alignment. That was another like, no, stop, back up.
Oh boy, I see we're going to, we might lose some
oh dear.
more optimizations in the CPU.
Yeah. This is another stupid story. So you should stop me in my war stories. This is the first silicon came back from Taiwanese silicon for H2O for Azul systems. This is the giant. So this is 24 cores on the chip. There were a bunch of screw ups in the silicon, as pretty much expected from first silicon return. We were trying to diagnose and get things running. One of them was the registers, the register bits, the 5 register bits were getting pumped through the instruction branch predictor decoder thingy. And he was fetching instructions based on register number leakage and then making predictions on them and then trying to go and execute them incorrectly. And the fix in the end was that we had to lose a register bit. We just JIT to 16 registers, all the even ones and not the odd ones, in order to save the jump branch predictor from getting too eager. I don't know, but yeah, I can totally see all kind of weird things here. So they're getting data values in registers, no doubt because of some prediction that comes around because it's in a register and I'm going to fetch on it or something, who knows what. Yeah, this comes around to, another sort of shared memory, like I really like the shared memory. When we couldn't make silicon go faster, I like the shared memory multiprocessing over distributed, but the fine granularity is a lot more efficient. But in a multi-tenant situation, obviously every fucking thing is leaking. And now you have to decide what your security risk is. And maybe it is, you have to go to like services that are disjoint physically, not just running in different process space. They got to be running on a different piece of silicon to avoid the leaking, and a seriously different piece of silicon. So you have to pay some serious overhead of, you know, fucking TCP socket and a Ethernet cable, or else you leaked. And you can still leak there, but maybe just leak a little slower. I don't know.
And the thing is that once you want to run fewer things on a single chip, then Intel's advantages start disappearing. And that is causing them a bit of pain. That is why you see one of the reasons why you see some movement towards ARM.
Really? I just thought the ARM guys were all about like buckets and buckets of wimpy ass chips.
Yeah, but that's what, if you're running just say one tenant,
yeah,
on a tenant, then you might as well make it a wimpy one.
Cheapest possible. Well, this gets into a whole different design pattern where I physically want to have a chip for security, but I want to have them Ethernet together somehow. And so they want to be wired, but they're their own one core, one socket. But I'm only talking not through memory, but through TCP on a single wire. You know, that's actually getting pretty close to what Zool was doing. They had X-links between the chips. It was a serial protocol. You know, 16 die, but you can only fit so many on a board. And so we had a stack of boards and stack of dies per board, and they were all symmetrically hooked up with X-links. Kasler, what is Kasler? Sorry, I'm not up to snuff on the jargon.
Kernel address space layout randomization.
What's the K?
So it's K is for the kernel. It's similar to the user space where it's just ASLR, where you have the addresses of the segments in your executable when it is running randomized.
Yeah, right.
Which, when it was enabled, that was really fun to debug when you weren't used to that, because you got used to certain things being at certain offsets, and then suddenly that wasn't the case anymore. So that was fun. But in any case, it used to be a relatively simple idea, but the way it is implemented in practice is basically a collection of patches upon patches upon patches, and I'm not quite sure whether anyone really knows what the entire set of the interacting things is doing at the moment, and the security benefits compared to the cost of this complexity may no longer be quite justified.
Yeah, it's not balanced anymore in that sense. Yeah. Welcome to the new world order, where computers have their limits, and one of them is way too much sharing. Fine.
So in the cloud, actually, this issue is even more exacerbated, right? Because you have no control of who you are co-located with. And once you start going that path, actually reasoning about performance kind of becomes even more difficult.
I guess I just said it goes the other way in a sense. It's like address space layout randomization. You have a random neighbor. Because you have a random neighbor, the attacker is unlikely to be your neighbor unless almost all neighbors are attackers. So you're likely that your neighbor is an asshole, but not a malevolent one. And then of course, you know, performance sucks because you have no clue and no one has a clue. And yeah, I've done big performance work on cloud stuff. That was H2O. Put a 100 node cluster together and go try to do a logistic regression on some giant ass data set. Somewhere, somehow, some set of nodes are fast and some set of nodes are slow, and it randomizes left, right, up, and down. And big data, big nodes that eat all the memory. So then, you know, Amazon's happily jamming 2 such nodes on the same physical hardware, except there's only memory for one. So it swapped the shit out of the other one. And it's just like, what the hell? I don't know how you design an implementation for, you know, reliable performance in such a scenario.
I didn't think that they used swap.
They did something bizarre, and I don't know what it was, but we definitely had issues where we had multiple nodes. They would launch because it's a JVM, and you would launch on the same node, even if you said XMX, God knows what. And then you actually used it all, and then suddenly they blew out, right? And something got super slow. And we eventually had to go find another button you could press on Amazon that said, no, no, when I said this, I meant it. I'm not just kidding here. Because the assumption was, oh, hi, Kat. The assumption was, I guess, was you said XMX 64 gig, but you didn't really mean it, and you were actually only going to use 2. So we'll just share with all the other guys who said XMX 64 gig and only use 2. Except that we would use the 64 gigs, and that would be the end. Go down in flames.
So I know they over-provisioned the CPUs. I'd never heard that they over-provisioned the RAM.
They definitely did for what we were doing. I don't know. This was 5-6 years ago. Put 100. We were trying to eat a 7 terabyte data set into RAM, so we had 16 terabytes across the cluster, which meant that we had, I don't know, however many gigs per, and we asked for big nodes and a lot of them. But not the super giant ones. They had fewer choices back then too. So it wasn't super giant nodes, but there wasn't 8 gig nodes. They were like 64 gig nodes. And we asked for 100 of them, 128 or whatever. And then lo and behold, we got them and we started loading the data. And shortly, a bunch of them choked. And we decided after the fact that they actually lied and didn't give us the things. And they're all of the node got shot down, so just start another one. But we didn't run a cluster with redundancy that way. It was every node took a unique piece of data, and you couldn't just shoot a node down and start it. So it took a while to get them to actually give us what we asked for up front. And I think they may have changed policy since then. I don't know. This was like people in the land of Java were all the time doing, over provision on memory over what they needed, because no one knew how to handle leaks and out of memory or not out of memory or spikes or whatever the hell. So they all over provision. That was in fact Zool's business model. That we did all kinds of stuff on that. The big hardware, the OS was really good at sharing memory between heaps independently of what you said. We would look at what you were using, and you could ask for the guarantee that would get you everything you said. And then we had people who would say they would take extra, but if they weren't using it, they wouldn't get it. But if they wanted to use it, they were allowed to have it. But if somebody who said he wanted 64 gigs and demanded it actually needed it, your process had like 10 milliseconds to give it up. And the GC cycle could run in that period. And if the GC cycle, one talk of the GC cycle could pull the memory back, it would, and hand it off. And if not, you got it out of memory and died. So we had I won't say funny money, but we had an ordering to the processes, and we were allowed to share. And
It sounds very, very familiar.
Oh, good. Well, there you go. So we had a time limit on how fast you had to give up your memory. If you were loaned memory for the OS, basically if you were loaned memory for the OS, you had a time limit, you had to give it back. And the GC cycle could run just barely in that time limit, the minor cycle. If the minor cycle could do the job, then you're allowed to carry on. And if not, you got blown down. And that was a known accepted behavior for a bunch of clients who bought a big $1 million piece of hardware and had some critical jobs that just had to go, and a bunch of batch jobs that they could restart or rerun or cluster up, or they didn't care. So it was a useful thing. And there's another one of these OS user mode cooperations. I did a lot of hardware software co-design. Well, this is an OS user mode cooperation design.
So speaking of which, anyone have experience with anyone besides Cliff, because I know you do, experience with building in Safepoints to generated code?
What? Building?
Safepoints.
Yeah, no, I know what Safepoints are, but what was the question?
Building them in as you generate the code.
You mean the polls?
For example, yeah. I mean, when you have to, there's not a lot of literature on the topic, right?
You want my answer or not?
Noob question, what's a save point?
Save point is a point where the JITted code will agree with the state of the Java virtual execution machine. And in between safe points, the JITted code and the x86 CPU have no correlation, vague correlation to the Java machine state. That's where your performance comes from.
So like calling convention stuff or like whatever?
Yeah, vaguely. A calling convention is a point where, yeah, very much. A calling convention is a point where you all agree that there is a layout of program language semantics for variables that is agreed on by the caller and the callee by jamming them down into fixed registers. So there's an agreement made, and in between the calling convention points, there's no say on where things landed in hardware. So same thing in the JITted code at safe points. You are allowed to claim there is a particular execution point in your Java program that you understand. And as such, you can now do other things at that safe point, like load classes that are not allowed in the sort of the general, I'm just running random shit. Like in between safe points, the Java execution machine state is not defined. And so I've loaded and stored memory out of order, and I've loaded and stored values and registers out of order, and I've elided dead code, and I've done all kinds of funny games with your JITted thing, and I've done loop invariant hoisting and pre-computed and post-computed and blah, blah, blah. Things are not the same. So I can't stop at a random x86 instruction and say, hey, and now load a class, because the class will say, and hey, I expect you to be at some bytecode, but you're not at any bytecode. So that's what a safe point is. Layered on top of the typical safe point is also an OOP map used for garbage collection. And so GC cycles also take place at safe points typically, but there's no requirement that those be overloaded. Does that make sense?
That does make sense. Thank you.
Yeah, and the reason that you brought it to mind was, well, first because it's a problem I'm working on, but second because the when you're doing user mode fibre management, safe points become quite valuable. So
that's your fibre change point as well.
Can be, yep,
Yeah,
exactly.
it can be, yeah. Yeah, so to Zool, we layered onto the safe point notion a whole lot of other things. We could stop individual threads because they did a load compare branch, which on the x86 is like half a clock, highly predicted. And then they would jump into the user mode handler, and they would go load up a word which contained all the things, self-service tasks that we're supposed to do at this safe point. And that would be all the things that would make sense and a bunch of shit that you never thought of that you have to handle. So crawl your stack for oops, store oops into a place the garbage collector background thread is going to pick up. Take a lock, count your locks for bias locking, unlocking. Some thread can throw an exception at another thread. So this thread over here can throw a JDBC driver not found on that thread over there, who has to honor JDBC driver not found. It's like, what the fuck? I never heard of a JDBC driver. He still has to honor it. And that happens at a safe point. There's usually you throw thread.death because you want to kill that guy. This guy wants to suicide, but you can throw any exception you want, including things like null pointer exception, which the JIT has very carefully, worked very hard to remove all possibilities and all this kind of shit. So that's annoying. There were like 15 or 20 of these self-service tasks we had at safe points. And you had a different question, Cameron, which is where do I put them? Or how do I inject them? And I have a different comment, which is there's a trick to optimizing the hell out of them so that they don't cost you performance, but you have to put them everywhere there's a loop or you'll have a long running execution point for which you have no safe point and you can't load a class, or you can't release a bias lock, or you can't throw an exception on somebody, or you can't do blah, blah, blah. And we used them actually like Stack Overflows as well. So we had a guard page at the end of the world, and it guaranteed that you would run across a safe point before you bumped the stack more than 4K. So you hit the guard page and you release the guard and you set the bit, and then you ran on until the safe point happened. And then in the safe point handler, you said Stack Overflow.
Right, so I posted the code from Hotspot, and there it you just do a test instruction against some address.
Oh, this is the new thing. Yeah, Zul did a test in, right, okay. Instruction. Here we go. Racks pull. So for us, we did it per thread, and we guarantee you that the thread stacks are all aligned. So you move the stack pointer to a standard register trim the low order bits and then test. So it's an integer move and an integer and then a test. Otherwise identical.
So we call that handshakes, like a per thread safe point is what we call handshake.
Yes.
And we now have those, and we're moving much of the stuff from safe points to handshakes.
Okay, yeah, we gave up on safe points at Azul from the get-go and just said everything's a per thread safe point. And then you can do ragged safe points instead of a global stop the world, and you have a bunch of options. So this is the Azul collector doing this, you know, a decade ago. So you guys are going to get there eventually. Bias locking is another big winner because you can unbias a lock without having to take a global safe point.
And Ron, you're working on Loom, right?
Yeah, well, Cameron, here what happens is that you install a handler, an interrupt handler that catches this. It checks the instruction whether it's an actual safe point. There's some metadata in the code, and if it is, it jumps to the safe point handler. I can send you a link to that code as well. Yeah, but I'm saying yes. In general, hotspot we're moving gradually towards handshakes, and also. I've been told by the ZGC people that probably this year we'll be at a point where we scan 0 oops during any thread pause. So nothing is done in safe points or handshakes. We just start the thing. Even stack scanning is concurrent. All the internal hotspot data structures are now in the process of moving their internal oops to some shared location that the GC knows about and can currently change them, etc.
It's impressive.
Yeah, I did this a decade ago. Oh, it's good. I hear it's happening finally. Now, more like 15 years ago. This is a long ass time ago. It was my first big hack at Azul.
Yeah, but the problem that the Java guys have at Oracle is they have to unwind all this awful code that some guy wrote in the late 90s.
You know, you had to figure out how to do it at all, and mistakes were made. And I was not allowed to unwind it while I was at Sun, and Azul said, go to town. So I unwound that shit at Azul, and I was not allowed to unwind. And then I tried to give it back to Sun, and they would not take it. It's fine.
Wait, you thought I was talking about you?
I'm conceited that way, yeah.
But Cameron, let me tell you something about preempting fibres. So most of the time, you don't need to do it. It's very rare that you need to do it. So fibres normally, what they do is, you know, they process transactions. They either wait for I/O or for messages on blocking queues from other fibres. So it's very rare that you have a fibre that actually is CPU bound. When you do, so currently it's optional. We allow custom schedulers that you can plug in Java. You can plug in any executor, but it will be possible for the custom scheduler to preempt a runaway fibre at a safe point, actually in a handshake. So just that kernel thread will trigger that mechanism. But we don't expect it to be very useful. The problem is this. The reason why this sort of time sharing is very good for OS threads, but not necessarily for fibres, consider that you have, say, I don't know, say you have 10 cores and 20 threads, and I don't know, 8 of them are very CPU heavy, processing bound. So occasionally you'd like to preempt them to run the other. So you have 2, so I don't know, the other 10. But if you have 1 million threads and I don't know, 40% of them are CPU bound, then you're under provisioned by a factor of 1,000. So you need 1,000 more CPUs. So in that case, no scheduler will save you, no matter how many preemptions you'll do. So the only case where it is useful is if you have a small number of fibres that are actually CPU bound, but they somehow bother you enough because we use a work stealing scheduler and it should sort of smooth things over. But if you have just enough fibres that are very CPU bound, then it could be a problem. And only in that rare case should you preempt something. So generally, as a general mechanism, it's not as useful for fibers if you have 1 million threads as it is if you just have 50.
So the obvious fail here is that I ask for how many CPUs I have, and I launch as much work concurrently as I have CPUs. So they're instantly all just exactly consumed. And then I have all this background shit I want to do, like GC cycles and stuff. And so preemptions just has to happen all the time. And your statement of I have to have a particular count is true, except that the obvious thing to do is that I'll immediately ask for the very particular count that will cause you grief.
So if you know, so the story is this, if you know in advance which threads are CPU bound, don't make them into fibers. So it's just a choice of use kernel threads for those.
I'm talking about standard programmer mindset. Fibers are awesome. I'm programming in fibers. I'm doing them because I have a big job and I want to use fibers for whatever. The first thing I do is I say, oh, how many parallel iterations of my machine learning algorithm do I run? Well, okay, as many as cores I have, boom, done. Now I have, total CPU bound, whatever, 20 cores going. I'm just saying there's a sweet spot that people will drive right at, and so you better have an answer for handling 20 plus 2.
Right. Yeah.
Been there, done that.
Oh, and by the way, that speaking of fibers, so a few weeks ago, I wasn't here, but somebody pointed it out to me. Cliff, you were talking to Kirk, who was asking, why is it that fibers help? Isn't it all about context switching? So because of that, today I wrote something that explains that it has very little to do with context switching costs and everything to do with the number of fibers that you can spawn. So I wrote that.
Yeah, it's the number of fibers, right? That's
Well, fibers have one other unbelievably nice benefit vis-a-vis a thread, which is you don't get trapped under your own stack. So
yeah,
anytime you can get trapped under your own stack, you just create a new fiber and you're done.
At H2O, we had this thing where you would have the core, whatever, the running process fork, join, and block and wait for his child to fork underneath him and underneath him, except it would go around the cluster in a cycle. And you could be caught behind yourself via a set of indirect remote accesses that went circular through a cluster and came back to your own node. And we had a lot of games we had to go do to go validate that you weren't getting stuck that way because we got weird deadlocks and sort of spewing of tasks because of that. There's a lot of cool stuff going on in the chat today. I put these videos up on YouTube. I should throw the chat on. And
yeah, especially with Matt back. We're going to get a bunch of links.
Well, it's all good. Yeah, fine. I'll have to figure out how to do that one because the standard chat window, whatever, discussion on YouTube is like 5,000 characters, which, we're going to run out here. So I'll figure it out. It's fine.
I'm actually curious about this. Have any of you heard about this? Maybe Ron, because that seems to be your area, the recent patches from Google about user-level threads.
About what going on here?
User-level threads in the Linux kernel. So not M-to-N threading, but bringing benefits of M-to-N threading to one-to-one threading. And it's been a very long-going process. They had a presentation about it in 2013 first, and they just uploaded the patches very, very recently, a few days ago.
Yeah, so the thing is, the problem is that helps reduce the context switch time, but it doesn't help increase the number of threads you can have.
Right, and the thing that Fibre says is we can have 1 million, and most of them are blocked most of the time, and we don't care.
Okay, so it's more of an optimization of an existing solution rather than a more substantial change, if I understand.
It's right. A dramatic optimization. Right, so this is one of these things where size matters a little bit until you cross some 10x threshold, then it matters a lot more. Right, it's all the reason Godzilla, he's just a little bit bigger, right? No, it matters.
Right, interesting.
You did this is where React came from. The whole React manifesto. It's the cost of spawning another thread that's going to block and spawn another and another and another kind of thing sort of got so big that was your dominant cost. And that if you had one physical CPU running, but a bazillion lightweight things that would just block when they did and get callbacks when they came back, you know, life got so much cheaper. You had this new model of thinking and a new way to solve problems. Same with H2O doing giant, big parallel stuff. We launched 1 million fork join tasks, 1 billion fork join tasks, and that was okay. They behaved like a thread when you were coding, and they behaved like a super tight, but they were basically a fiber, except I had to manually do all the blocking hacks. But it was a very convenient model to code against, and it had the good performance. Couldn't have done it with a user mode, OS mode thread. The costs were too high. So Cameron, did you get your question answered about Safepoints?
Well, my questions usually take a couple months to answer because I have to go off and read 100 pages offline. And
okay, because what you had asked for was not what I answered. In particular, there's a stupid easy hack I do for performance optimization on Safepoints that was totally new at the time I did it, and now of course it's been around for 25 years. And you should do the same hack, and that's represent the Safepoint in the compiler IR directly as if it's a very low frequency branch around a call that takes all live machine, virtual machine values and produces whatever values are going to allow to be changed at a Safepoint. And then let the optimizer go to town, where you teach the optimizer shit about branch frequencies and execution frequencies like. And at the Safepoint weird call, you
so
teach
basically
it.
It looks like a random if that pops up every now and then with a push a pop a.
Yeah, you put a push, you insert in the code an if that has a predicate test, which is the Safepoint test, which you don't specify in the code because you're going to change, you're going to tweak it constantly. Less like Hotspot's been doing here in the chat. You look at that, you tweak it for a while. The key is there's a branch with a frequency, and the call target is a function called semantics, but the ABI can have anything in any register because you're going to handle that with mapping. And when I say any register, I include stack slots for spill code as registers, so that the register allocator is encouraged to spill things that are only kept alive for Safepoints onto the stack. Spill early, spill often, get them out of the way. You have an infinite number of stack slots to be spilled into. They're very cheap to spill, it's just a store. And then it's there for a Safepoint should one happen, but it doesn't cost you anything other than the compute.
So if you're in a tight loop without a condition, say you're in a while true and you're trying to generate code.
No, you're in a Fortran loop doing a stencil calculation. For I equals 1 to bazillion,
right.
Add elements. Yes, exactly.
And so you want to put a Safepoint in there. So what's your
okay, so now so there's a bunch of
give me some x86 assembly. Would you use a CX with a JZ or wait, is that?
No. So the wrong mindset. You got to up level. So I will put in the IR the Safepoint test, whatever the fuck that's going to be. If it burns a register, then it's going to get allocated a register. Fine. I don't know what it is. Okay, no, wait. That has costs because I have to compute the machine, the virtual machine execution state at every pass through the loop. But suppose the loop's doing a DAC speed, and it's load array, ADB, add them, store and see, whatever find it. So it's like a fucking tiny loop. So load, add, store. That's 90% of the work is the Safepoint now. And how do I reduce that cost? It's the Safepoint semantic cost, not the test itself, but just the act of executing. I have to know I have I indexed or J indexed or whatever. All the indices have to be computed. Okay, you have to get rid of that. So you unroll the loop. And you
unroll it 16 times or whatever.
And you allow the multiple Safepoints to collapse. If I have a Safepoint in the prior iteration of the loop, then I can say it dominates and throw the others away. All right, there's this very specific Safepoint optimization hack that says I can't get rid of the last one in any looping construct, but I can get rid of all but the last one. So it's not quite the same as a standard dominating test. It's like a null check. It's not quite a null check. It's close though. You know, that's sort of the first major piece. And the second one, you get more fancy and do unroll and jam on those kind of loops. Eventually I went to unroll and jam, which, you know, do or don't do, whatever. I don't know how far you want to go. If you're using LLVM, he should do that kind of shit for you. You just have to teach them the fold up rules on Safepoints. But you totally want them to unroll that loop and then fold the extra Safepoints away. And that drives the cost of the Safepoint down by as much as your unrolling factor is. So you unroll by 16, you divide that cost by 16. So now it's 2, 3 clocks, divide by 16, fuck, I don't care, right? It disappeared in the noise.
It shouldn't be 2 or 3 clocks.
Yeah, I mean, way over the top. So it's usually 1 clock, right? But it could be 2 or 3, but I don't care anymore because I divided it by 16.
Right. If you're using LLVM, you can even use the what I think Azul committed into LLVM, which is state points, to have Safepoint inserted in for you.
Okay. Okay. So
and just Safepoint, like we have done that for Mono in like 2 years ago or something, and it's only used to insert Safepoint, nothing else. Not the whole GC read, GC write, and all of that. It's just Safepoint.
Yeah, right. So the only issue there is the compiler has to understand the semantics of your Safepoint to understand how to insert them correctly. So it's not just once per loop, but recursive calls have to have them once per recursive call cycle. And sometimes you want them more often according to the cost between the delay between Safepoints. So if I have a loop and I say it executes whatever and I put them 1 per loop, but then I move it out of the loop and then the loop runs for minutes, I don't get a Safepoint. Okay, that's bad. And I can do unroll and jam and say, for every X iterations, I then do a Safepoint outside, but it's the unrolled and jammed version. And I can dial the time between Safepoints. I have to pick that number and teach to the compiler. Okay, that's one piece. What do you put on the Safepoint call? So you've inserted a Safepoint. What happens on the off branch? You have to capture the program, the high level language semantics, not the IR of the moment, which you're happily optimizing the shit out of. But you have to capture whatever you can see in a debugger, right? And then if I'm going to allow you to write here, then you have to actually have the writes feedback in, but you actually would rather break out to the interpreter. I don't know. So I'm not saying the LLVM can't do it. I'm just saying it's got to be a good match, and there are a bunch of things that are difficult.
So we did that in Mono, which is not Java, far from it.
Yes.
So what playing the advantage of Mono is that it doesn't have the whole oopmap concept, and it's all just conservative GC. So there is no precise or anything. So it's just easier. You just don't move object and you're good to go.
Yeah.
So that playing in the hand, and that would probably not work for Java, and that's why Java needs state point and GC read, GC write, and all that kind of stuff.
Yeah, the GC read write is different from the Safepoints. I was saying the GC, they don't have to be stacked on each other, but it's convenient. But then you're doing it.
So what's the complementary to state point to create a oopmap? I don't remember what the name is.
The Safepoint, sorry, is a point where you have the program semantics match the layout and the hardware.
Yes, but so you use oopmap in Java, you use oopmap to store that.
No, it's the other way around. You have a Safepoint because you have to for semantic correctness. You then add an oopmap to it. So you don't store the oopmap with the Safepoint. You store the oopmap with the Safepoint, Safepoint with the oopmap.
So the oopmap is basically the state of the object of the variables in the
map, not the oopmap, the Safepoint map.
Okay, sorry.
Yeah. Okay, you got it now. Boom.
Yes.
And Ron, any impact from, because you was mentioning LLVM, any impact on the loom work from Grail? Is that how does that complicate it, if at all?
Graal, you mean?
Yeah, that's the one.
So currently, so we hardly had to change the compiler. So Graal just works. But if you're talking about substrate VM, which is Graal native image, that would require a different implementation. That's a different team.
No, I was talking about the farmer.
Yeah. So in OpenJDK, if you use Graal, it just works. We added a couple of intrinsics, but there were very few and minor changes to the compilers we had to do for Loom.
Cool.
By the way, that's the problem. That might have driven some of the design because we have so many compilers and back. So we have one interpreter, we have C1, C2, and Graal. So we have 4 execution engines, 3 of them are compilers. And if we want to make a big change in the compiler, we have to do it in 4 places. So it's a good reason not to do it.
Yeah.
I wasn't sure how intrusive the fibres work was into the VM itself.
So it was much of the interesting work was in the GC rather than the compiler to do some of the fast context switching. We had to do some interesting stuff for the GCs because we don't want to. So here's the thing.
You're mid-copying stacks.
Right. So here's the thing.
Partially.
In Java, and this, in fact, this ties a few things here together. So in Java, when you want to, so you can have references, or oops as they're called in Hotspot, you can have them inside objects on the heap, and you can have them on the stack. And on the stack, in the traditional GCs, they're scanned during a safe point. And during a safe point, we walk the stack, find the oop maps at each frame, and then mark the oops, and then we'll release the thread and continue doing things concurrently. This work is now starting to be done concurrently, but that's the idea. The problem with objects on the heap is that the location of the oop inside the object is not allowed to change dynamically. Some of the GCs, in particular, I think G1, has a very strong assumption that if a certain memory address has ever had an oop in the current cycle, it will forever contain an oop, where forever, I think, means in the current cycle. So you're not allowed to have objects that dynamically change where you'd store a primitive where there used to be an oop. And stacks change very quickly. So then you have the question, now you have 1 million stacks. Do you want them to be GC roots, as in Golang, that's what they do, or not? But if not, you have to somehow deal with that limitation that the GC cannot have an object with a mutable shape, where the shape means...
Color your stack slots, oopish or not oopish? And force the JIT to only throw oops down in oopish slots?
Yeah, but then, so that was one of the ideas, but the realization was that that would require a big change to the compilers. So,
well, changing the registrar allocator. C2
yeah,
should swallow that one just fine, but I don't know, C1 would be a different animal.
I think there was some discussion around that, and I think the understanding was that it's not as easy as it may sound. Plus, so let's. I can't go into all the details because it would take too long. But let's say, let me explain why that's not good enough and why we can do so much better. If you have, so now you have a stack that you want to save somewhere, and you need to know where the oops are. And their location can't change. So the thing we did originally in the first prototype was just every time we wanted to yield a fiber, we just walked the stack, found the oop maps, extracted the oops to a separate object array, and copied it to the heap, where the GC would just look at the object array and would reconstruct everything when you copied back. The problem there was, first of all, that we had to find the oop maps, we had to parse them, and that took a long time. We want to do that millions of times a second. That's just can't be done. So we played with some stuff. For example, instead of parsing the oop maps, we would have them generate code to do that work for us.
I'm sorry, what do you mean by pause the oop maps?
Parse.
Parse the oop maps. Yeah, okay, fine. Yes, fair enough.
So doing that in C code and loop would be slow. Right, so, but what's worse, and that is why just putting the oops in certain locations is not good enough. What's worse is that just finding where every frame begins and ends takes too long. Because the only information on the stack is a return address. And once you want to have some metadata about it, you have to, even an indirection, and we put a no-op where in the code where the return address points to with the size of the frame. But on Intel, there's a separate L1 cache for instructions and for data. So if you do a move instruction to look at where a return address points to, you want to read the no-op with the metadata there, that's a cache miss, an L1 cache miss. So all that is just too expensive.
We did it a different way at Azul because we totally had cheaply crawlable stacks. There was a thing we were doing there to go, I'm trying to remember exactly what we did. We guaranteed you that you could crawl the stack at more or less 1 or 2 clocks per stack frame, not parsing the OOP maps, just crawling the stack. Because we did this low cost, high resolution stack crawl constantly for doing performance profiling. We had random stack sampling. So random interrupt, you'd stop, you'd crawl your stack, collect the low 8 frames, throw them in a buffer and move on. That would not take very many clock cycles, 100 clocks or less in and out.
So
there is a way to crawl your stacks cheap.
So you need to inject data into the stack itself, don't you?
No, it was not injected into the stack. I'm trying to remember what we did here. It might have been, I don't think it was. I think we grabbed a return address, and that had enough information that we could get the size of the frame in one hit in a cheesy hash table that was pretty damn quick to go after.
Yeah, so it's not bad, but it's an L1 cache miss. It's a guaranteed L1 cache miss.
No, because the hash table sat in your data L1.
Why would it sit in your data L1?
Yeah, because you were profiling often enough that it was coming around. It wasn't always there, but it would be in your L2 than versus L1. Like I said, the entire time to crawl that stack for the 8 frames deep was so low that we couldn't measure it reliably.
So we've thought of doing that, and we've thought of injecting, having the code stream preload that metadata, but then we had a different idea of just changing the GC.
Yeah.
And, what we do now, we take advantage of the fact that the limitation I said before, that the shape of an object cannot change, for the generational collectors, that is only true in the old generation. In the young generation, because it is actually collected at a safe point, we can mutate it. And we teach the garbage collector to do that scanning. So if the fiber is hot, it will be allocated in the young generation. So what we do, we allocate in the young generation, we just do a mem copy. We don't parse the stack at all. We just copy a portion.
The self CPU running, the current thread running copies his own stack, right?
Yes.
Yeah, okay.
And a small part of the stack. It's just a very, very fast mem copy. And then it's in the young generation. And then the GC does the stack parsing when it needs to. And we copy it back. Once that portion of the stack gets promoted by the GC, then it becomes frozen. You can only remove frames from it, but not add. Next time you want to add stuff, you need to allocate a new chunk.
Oh, I see.
And
yeah, you're actually crawling your stack a lot more frequently than I think I ever did. I think that's part of the difference.
So it turns out that you can do, so if you, as long as your fiber is very hot, you just mutate in the young gen with mem copies, and it's very, very fast. Once the GC kicks in and promotes it, and your fiber is obviously colder, then you do some other stuff.
Why would your fiber be colder just because the GC promoted you?
Oh, it could also be an accident, right? But no, I'll tell you why. Because if you say it promotes you by accident, you can still just do a mem copy if you want to context switch into the fiber. You just do a mem copy from the old object.
It's fiber, right?
But next time you want to context switch out, you allocate a new one in the young gen.
Yeah, right. Yeah.
So the
Sorry, you had said a thing that was a misspeak in causality, but the obvious answer is you're always mem copying into young gen because you test for it and guarantee it.
Yes.
Fine. Okay.
And for the current collectors like ZGC, we also turn out to have a certain grace period. And
okay. So GC then parses the OOP map for these kind of objects. So they're not a classic Java object. They're a stack frame object, have different parsing rules.
Yes, exactly.
Yeah, fine.
Ludovic, are you still working on Mono?
I switched to Java 12 months ago, 15 months ago. The question I had for Ron was, what's the allocation rate of these chunks? Because it seems like if every time it gets promoted, then any old chunk needs to leave as long as it leaves, and any new chunk needs to be allocated in the young gen. You're going to allocate a lot, especially on the heap.
So the answer is that it's much lower than any other alternatives.
Okay.
If you do, suppose if you use reactive streams, you allocate a new object every single time for every stage of the operation. If you use Kotlin coroutines, they can't do this mutate. They don't have access to the VM, right? So a Kotlin coroutine would allocate a new object every time a task switches. And here we do it once per GC cycle. And that could be once every few seconds. So our allocation rate is actually very, very good. And in some respect, it's better than doing asynchronous programming with callbacks, because we mutate the stack in the data without generating, without allocating a new heap object with the data we want to transfer from one stage of the pipeline to the next.
You're gating your allocation rate by the garbage collector and not by the execution speed.
What's interesting though is that it's going to make it, what that implies is that simply calling a method might allocate without even having any new or any explicit allocation. So how you, for example, like I know Cliff talks a lot about like HFT, which should not allocate, or should allocate as little as possible. How is that going to impact this kind of workloads where people are very conscious about where they allocate and when they allocate?
So first of all, you allocate, you potentially allocate when you yield, not when you call a method.
Okay.
It's up to you. So the answer is, if you don't want to allocate, don't use virtual threads, because they store their stacks on the heap. If you don't want to use a heap, don't use it. But I think there is something funny. I saw that applications that are sensitive to allocation rates are actually optimized for all GCs, like parallel GC, because parallel GC only works when it wants to collect. But a GC like G1 and ZGC, they have barriers. It can be cheaper to allocate than to mutate in many cases. So some applications that want to optimize for Java by not allocating are actually doing the wrong thing with new GCs.
Okay.
Yeah, H2O was very comfortable with the old parallel GC.
Yeah, if you use parallel GC, then not allocating or allocating upfront, that's the best strategy, because you don't have any barriers.
The other thing is we just allocated the big data in big byte arrays. So there were very few counts of objects and a very large count, medium count of very large objects. And that was where all your heap went. But those large objects GC instantly quick.
And you wanted best throughput, not latency.
Best throughput.
Yep.
Yep. Every now and then you took a full GC and it was never too bad. Even on giant, we had 256 gig heaps. It would never take very long. Fork join tasks were like fibre stacks. They were tiny little objects, and you made one every time you forked a new task, and it lived until that task completed. And that was sort of the cost. And those all died in young gen very cheaply.
I have to go.
Yeah, I think we're at a good time here. Does anyone else have any comments? And Flavio, I saw you came in, but it's an hour late. We're winding it down.
Yeah, I was hoping to join earlier. I couldn't.
That's okay. Speed test, yes, I know. So you folks don't know this, but see, my brother and I in Georgia, we play Halo every night at 11 o'clock on the dime every night. AT&T cuts his connection. It's just reliable as all hell. So we just have to, in the 20 minutes a game, so we just have to time it, and we look and we decide, no, start another one or don't. Let's wait till the bewitching hour and everything gets, whack.
So Comcast actually will try opening a speed test browser window, because they actually, if you're going to they have a list of sites that if you go to, they'll prioritize your traffic to try to make your account look faster than it is.
I'm well
speed
aware.
test is one of those.
I'm well aware. I've hit that. So I did this thing with Hydras, a Russian live cast conference. So we did a speed test to this Russian, jug thing, right? And I could not get a reliable read out of speed test, and it was just Comcast. It's like blatantly obvious. I go download games, I go play with whoever, whatever. I look at my prediction, then I go do speed test. Oh, speed test is glorious every time. It's like bullshit, All right, Comcast, quit dicking around here. Fine. Okay, it's been good. It's been fun. Next week we'll do it again. Have a good evening, folks, or good morning, depending on where you live.
Thank you.